the logic is extremely powerful. So the structures I will call rich structures. And what you can express in such structures is related to the weak second order logic. There are known various ways to measure, in some sense, to measure how expressive is first order logic. For example, the classical elementary classification question by Tarski, the question is to describe in some algebraic terms structures B which are elementary equivalent to the structure A. So in this case, it's hopefully looking at the algebraic structure of B, you will see what kind of objects are describable by first order sentences in A. For example, if you take abelian groups, all Shmylov's invariants are first order definable, and that's enough to classify elementarily all abelian groups given elementary equivalent to given one. But in general, it's very difficult. So lately, it was proposed, not maybe lately, it's always was there, because people could not do quite often more than finitely generated case anyway. So elementary classification to consider in the class of finitely generated structures. So your structure is supposed to be finitely generated, and it requires to describe all finitely generated structures which are first order equivalent to B. And that's a much more manageable problem. So more specifically, it was introduced a notion of first order rigidity. It's with respect to similar statements which are coming from topology or geometry, like Mostovsky rigidity. So first order rigidity, the term I believe was introduced by Lubotsky and his co-authors. It's the following one. So A is finitely generated and B is also finitely generated. So A is first order rigid if first order equivalence of A and B implies their isomorphism. And that's sort of, in a sense, first order theory of A is powerful enough to distinguish A up to isomorphism in the class of all finitely generated structures. More stronger property is quasi-finite axiomatizability introduced by Nice, which means you don't need to have the whole first order theory of A. There exists just one sentence which describes A up to isomorphism in all finitely generated structures. So if finitely generated structure B satisfies phi of A, it is then isomorphic. So this is a very strong condition, really, which is different from first order rigidity. It is indeed stronger. And you can consider a few more things similar which are related to isomorphism. For example, it's the condition is whether the structure is homogeneous in the sense that if two tuples satisfy the same types, they realize the same types, then they're conjugated by an automorphism of A. So it's much stronger. It's but it's about elements, not isomorphic type of A. And another condition which comes from algebraic geometry over groups or over structures, it's isotypical rigidity introduced by Boris Plotkin. Suppose two groups finitely generated Suppose A is finitely generated, and suppose B is also finitely generated, and it realizes precisely the same types as A. Does it imply that B is isomorphic to A? So it's a different from first order equivalence. It's the same types. For many groups, it's known that they are isotypically rigid, but there is no, because it's recent, there is no even example of finitely generated non-isotypically rigid group. I believe it is, there is, but it's not known. Must be somewhere. Anyway, these are two another types of similarity with respect to first order properties. Maltsev went from the other direction, and it's about to test strengths of first order logic in a given structure. He proposed to see which subgroups can be defined by first order sentences in a given group, say. You can formulate it for groups, but also for rings, whatever structures. Instead of subgroups, you consider substructures. So it's not about isomorphic type. It's about what you can define in a particular structure by formulas, first order formulas. Actually, he asked for 3 groups, but then it was now Maltsev type problems are considered for arbitrary structures. Most of my examples will be around several objects, not to go very far. It will be 3 groups, 3 semi-groups, or 3 group rings. So the solution to Maltsev problem in the 3 group, it says that there are just few subgroups which are definable with parameters. Among proper subgroups, only cyclic ones and nothing else. All cyclic subgroups can be defined, but nothing else. The same thing for torsion-free hyperbolic groups. The solution is complicated, but it shows that the 3 groups, they allow not much in terms of algebraic objects like subgroups to be defined by first order theory. What you can define there are a lot of definable subsets, but it's related to algebraic geometry over 3 groups, which is complicated, but eventually you can do it, even though it's really a complicated thing. So it's about geometry and algebraic geometry. It's not about algebraic properties, what you can define. So you can ask a strange question: what are groups where all subgroups are definable? Just to see what is the opposite of a 3 group, say. And it's easy to see that finite groups, infinite cyclic group, and not much else you can see sort of on the surface. 3 abelian groups z to z, and z is my notation. It's sometimes, unfortunately, a ring of integers, but also it's an infinite cyclic group. So z to z is just 3 abelian group of finite rank. There, just few subgroups actually are definable, not many. So what else? And it's not easy to answer. To make it easier to sort out things which do not fit in this picture, you can ask even stronger question. For example, we say subgroups in group G are uniformly definable if for any n there exists a first order formula phi n on x1, xn, and y variables, such that this formula holds in G on elements A1, AN, and B, and only if B belongs to the subgroup generated by A1AN. So it's very, very uniform. You're given a set of generators, you plug it into the formula, and the variable here gives you the subgroup. Other infinite groups with uniformly definable subgroups, it's not obvious at all. If you think a little bit, it's kind of it's very strong property. Not free, not torsion-free hyperbolic, not Z. All subgroups are definable, but not uniformly. Not finitely generated nilpotent ones. Even actually in finitely generated nilpotent groups, you can define a lot of subgroups, but not all of them. So are there such groups at all? That's a question. And it turns out, yes, there are a lot of groups like that. That's strange, which was surprise to me. And yeah, I didn't say actually. What I'm talking about is based on joint paper. It's a chapter in a book. It's called Gakta Book 2, Model Theory. So there is a chapter written by Olga Harlampovich, Mahmoud Sahrabi, and myself, which called Rich Groups. So you can find all details there, but it's interesting that there are quite a lot of groups which were subgroups uniformly definable. For example, Baum-Slack, Solitaire, metabelian groups. It's one related groups very famous in group theory. Risk products of groups like that. Free metabelian groups of finite rank. Kiliv announced, he gave a sketch of a proof which works for free metabelian of rank 2. Unfortunately, it doesn't work for rank more than 2 because the module, the derived subgroup, which is the module over the abelianization ring, is not free unless it's rank 2. So you need to have much more technique to prove this. So it was done in this paper by us. Actually, I think that many other metabelian groups as well. I don't want to get into it, but there are quite a lot. Kiliv showed that Thomson group, he didn't prove that uniformly definable. What he showed, it's by interpretable with Z, and I will explain that implies uniform definability of subgroups. Then with Mahmoud Sahrabi, we showed that if you take SLN over many rings, I just mentioned a few here. It's Z, Q, or number fields, or ring of algebraic integers. If the size of the matrix is more than 2, then it's subgroups uniformly definable. And Abny, Lyubotsky, Miri showed that non-uniform higher rank arithmetic groups are like that. And Olga Harlampovich and Lopez showed that free non-abelian monoids of finite rank, they also have uniformly definable submonoids. Free monoids or free semigroups are kind of very simple objects. If you start thinking, if you have finitely many generators and then you multiply them, there is no any cancellation. How you can uniformly define subgroups? That's kind of strange as well. But then when you look at it, it turns out that it satisfies a lot of uniform definability properties. So for example, for any n, there exists a formula phi n such that if you pick n elements in G, and this formula holds in G, if and only if the subgroup generated by this element satisfy the corresponding condition. So for every condition that I list here, there is a particular formula. For example, you say the subgroup is free or free nilpotent or free solvable or whatever. It's finitely presented. It's strange things, really, not definable by first order formulas, really. It's residually finite. Its conjugate problem is decidable. You can write down a formula such that A1, AN satisfies this formula in G if and only if the conjugacy problem, the subgroup generated by these elements is decidable or polynomial time decidable. When you look at it, you realize that it's not about group theory. There is something else very powerful going on here. So it's beyond group theory indeed. So I would like to see what are the groups or structures which have the maximal expressive power first order logic. In the group that I mentioned above, you can express quite strange properties. So the first order logic is very powerful, expressive power of it. How powerful and where this power comes from, that's not quite clear right now. How one can prove that things like that. As I said, it's not group theory question really, because it's somewhere else. So a reasonable way to express it would be you can say the first order logic in G is as expressive as some more powerful than first order logic, some logic L over G. For example, you can say it's as powerful as the second order logic, all L omega 1 omega. That would be unreasonably powerful. But what is reasonable to ask, can it be as powerful as a weak second order logic? Actually, this logic would be perfect because whatever you want to describe to someone, big second order logic in most cases will suffice. The formulas are constructive enough and it's very powerful. So it's not just arbitrary second order logic which is too powerful. So now this comes the notion of a rich structure. Algebraic structure is rich if the first order logic over the structure has the same expressive power as the big second order logic over A. I need to explain what precisely does this mean. To this, I would like to introduce hereditary finite superstructure over A. It's well known. Anyway, I do it for a group, but it's for any structure. So you have say a group, and you define HF of A as follows. First, you define this set of hereditary finite sets. So PF of X is the set of all finite subsets of X. You start with A, then take A and all finite subsets of A and keep going like that. On each step, next step, you take what you've got and add all finite subsets of what you've got already, and then take a union. So the structure is this set, the predicate PA, which defines A of A. You can think it's actually as a two-sorted structure as well. And the only predicate is new predicate is membership predicate on the subsets. So in a sense, you can build all finite set theory, finitary set theory on a structure A, and you can use the predicate and operations given in the language on A. So the first order theory of this structure is the same as the weak second order theory of A. Okay, now I will make it a little bit more precise. The two-sorted structure, like here, you might have two sorts of perimeter variables, x1, xn, which run over A, and y1 capital, y capital 1, y capital 2, which run over the subsets. So a structure is rich. Now I can make it precise. If for every first order formula phi in the language of this structure HF of A, there is a first order formula phi star in the same variables x1, xn in the language of A, so it's a first order over A, such that for any assignment of variables into elements of A, AI are elements, this formula holds in H of A if and only if phi star holds in A. So over here, it could be not free variables using subsets. You can say there exists a subset such that for any other subset and blah, blah, blah. You can express a lot of things. But free variables are just elements in A. And that's a precise definition. What I mean by first order logic over A is the same or the same expressive power as the weak second order logic over A. The weak second order logic is, as I said, is extremely powerful logic. A lot of things you need, you can express in it. HF of A is a very nice way to represent the weak second order logic. But sometimes you need some other tools, some other ways to look at the weak second order logic. I describe here weak second order logic as a fragment of L omega 1 omega. So what the fragment is? You start with the first order logic in language L, you fix language L, and you build it up to this fragment, adding some formulas, phi. What do? You are adding these formulas, and by induction, you do two things. First of all, you extend the standard enumeration of formulas in the first order logic to the new formulas of the fragment you are building up. It's like Gödel's enumeration, nothing special. You can do it in many ways. And for each such phi, when you build a new one, you define the complexity of this formula. So phi I for us will be a new formula with index I. So we have the standard logical connectors, but also we have infinite disjunctions and conjunctions. So how one can build formula in this fragment using infinite disjunction and conjunction. So suppose you have a set of formulas phi, which are already built in our fragment. Phi are already built. So, and suppose it satisfies the following condition. First of all, the set of indices I is an arithmetic subset of n. It's defined in the arithmetic. And all formulas phi I have uniformly bounded complexity. And also you assume that all free variables are among a fixed list of variables x1, xm. So it's all free variables that occur they among x1, xm. So in this case, you're allowed to take infinite conjunctions and disjunctions, and you just need to define. You extend the enumeration, it's not a big deal, but what the complexity comes from the complexity of every formula phi r here, and complexity of the set of indices, if it belongs to pi s, say, then complexity of this new formula like that or that will be maximum of this complexity of the set of indices plus maximum complexity of the components plus 1. And also alternation of quantifiers adds to the complexity as usual. But this is a crucial how to deal with infinite disjunctions and conjunctions. So you build this fragment, and what Belayev and Teislin long time ago proved, Teislin called it Belayev's logic, but anyway, they proved that for any algebraic structure, for every formula of this fragment, there is a phi. There is a formula phi star in the language of HF of A, such that if you assign variables into elements of A, these formulas are equivalent. So every formula from our fragment LWSO has a corresponding formula phi star in HF of A, which is equivalent to this phi. And the converse is also true. So in other words, these two logics are equivalent over A for any A. So now we can use formulas from HF superstructure, but also we can use this fragment of the logic of L omega 1 omega. And it's convenient. For example, this example shows you that it's convenient to have both. For example, suppose you have a group. Suppose it's rich. For a given number, consider an effective enumeration of all group words in the variables x1, xn. Group words, it means you have variables and their inverses. And you concatenate. So it's words on this finite alphabet with inverses. So you enumerated them efficiently and consider the formula that psi n such that is disjunction of the very simple atomic formulas y is equal to wi on x1, xn. So this set of formulas, since enumeration is effective, it's a computably enumerable set. So it's arithmetic. I can take, so this is the formula of our fragment, which is equivalent to HF. Obviously, this formula uniformly defines in G all n-generated subgroups. Because it holds in G if and only if B is a word on generators, some word, so it belongs to the subgroup generated by this. So this gives you a very simple way to do uniform definability of subgroups, if the group is rich, of course. The groups I mentioned above, it turns out all of them are rich. It's not just subgroups uniformly definable. No, the first order logic in these groups is equivalent to the weak second order one, and this gives you a lot of a lot of definability properties and gives you QFA, it gives you a lot of other properties as well. How to prove that that a given structure is rich? To explain several kind of methods, I need the notion of bi-interpretability of structures. Yeah, before that, it's I mentioned groups which are rich, but there are a lot of rings which are rich. For example, Z, Q, number fields, rings of algebraic integers. There are a lot of commutative rings which are described. For example, free associative algebras, Laurent algebras, a lot. Actually, I believe that much more rich rings than groups, but also semi-groups. In the paper I mentioned by Olga and her PhD student, Laura, they proved not only free monoids are rich, but various one-related monoids are also rich. So how to prove that a structure is rich? One of the ways it's used by interpretability. Let me explain a little bit. So suppose you have two structures, maybe different languages. There is a structure A and the structure B. And B somehow is interpreted in A. It means this structure B. It means it's a subset of some A to the N. It's definable subset, and it's a equivalence relation which is definable, and operation on classes are defined by some formulas. So it sits somewhere here. And suppose whatever you can express in B, you can also translate into formulas in A, because it's interpretation. But this interpretation involves only the elements over here. So you can do a lot of things like in B inside the interpretation, but you cannot, for example, do much for elements outside. Now, suppose you have situation when B is interpretable in A, but A is also interpretable in B, like A star, which is isomorphic to A. So again, A star sits somewhere inside B to the N as a subset, again, like that. And whatever you interpret here, you can interpret in B. But it's very far from the whole B, as well as B is very far from the whole A. By interpretability, it means that if you look at A star, it leaves somewhere over here. And so it's, if you have an isomorphism, which is definable in A, so B is interpretable in A is interpretable in B, but it also, this little subset over here, it relates to, by theta, it relates to the whole structure by theta. So whatever you do, imagine now you have a subset, let me maybe subset, little subset like that here, which is interpretable in B. not interpretable in A, but it's interpretable in B. So it's interpretable over here somewhere. But then, because there is a definable isomorphism, it's interpretable, its image, it's interpretable in A. And that's the whole point. So, and this is the formal definition, precisely what I say. B is interpretable in A is interpretable in B, and there is an isomorphism of the interpretation of A considered as an interpretation inside A. This isomorphism is definable. And vice versa in the other direction as well. In other words, whatever properties, you can go back and define properties in A and B freely. And it covers everything in A when you consider subsets in B. By interpretability and mutual interpretability are different. For example, if you have Heisenberg group or UT3, unit triangular matrix of size 3 over Z, and the arithmetic Z, integers, ring of integers, each of them is interpretable in one another, even without constants. It's absolutely interpretable. But they are not bi-interpretable because there is no this definable theta here. And that's a big deal. In fact, this is true for arbitrary finitely generated nilpotent non-virtually abelian group. That's what we again showed in this paper that I mentioned. If you take finitely generated nilpotent group, non-virtually abelian, it's mutually interpretable with Z, but it's not bi-interpretable. That's why I said in nilpotent groups, a lot of subgroups are definable, but not all of them. Because there is no, yeah, but how it's related to richness. It's it relates by interpretability, relates to richness as follows. Suppose you have a structure A, and if A is bi-interpretable with HF of A, then A is rich. And that's sort of, if you think a little bit, you have a formula HF of A, in HF of A, you translate it in A, and as I said, if it's bi-interpretability, it covers everything. So you have an equivalent formula, first order formula in A, so it's rich. And that's the main tool, sort of. You just bi-interpret HF of A and A. If you work a little bit more, you will see immediately that structures, if A and B are bi-interpretable and one of them is rich, or suppose A is bi-interpretable with HF of B, then A is rich. And the corollary I'm going to use a lot, if A is bi-interpretable with a rich structure, it's again rich. So if natural numbers, of course, rich because HF of n is just, you just enumerate everything and it's definable in arithmetic. So it's interpretable with HF of n. And Z and Q, all of them are rich. So if you bi-interpret well one of them, your structure is rich. And that's what the results about groups that I mentioned, that was the method. Kelif and us and some other people, and also about rings, people prove that particular group or ring is bi-interpretable with Z. And that's good enough to be rich, or Q. I'm not touching here whether we're using constants or not. That's a little bit more complicated. By interpretability without constants, it's I believe is a rare thing, very rare. But you don't need this absolute by interpretability. It's enough to have in one direction, and also it should be enough when its uniform definability with parameters from a definable subset. So it's good enough like that. But don't think about it. It's right now. It's these are details. Now, the question is it always by interpretable with Z or Q or N? But it turns out not. There are a lot of rich structures, I believe more than just rich structures which are rich because they're interpretable with Z. For example, and this is the result I would like to talk a little bit. We proved with Olga Harlampovich a couple of years ago that if you have a free non-abelian group F and K is a field, then the group algebra K of F, that's a group algebra. It's you can see the formal sums of elements from F with coefficients from K, and you multiply and add as usual. So this ring in the language of rings and HF of K are bi-interpretable into each other. It's very easy to see that K is definable in this K of F, because K is just the center. It's all elements which commute with everything else. But it's very difficult to see that it's HF of K is bi-interpretable with K of F. So the group algebra K of F over arbitrary field is basically the same as HF of K. And in Novosibirsk school by Goncharov, Yershov, Andrei Morozov, there were a lot of study on HF of fields. So we can use a lot of them here to show which. Anyway, so these algebras are rich, and there is no Z here because K, for example, could be uncountable. So no chance to interpret in Z. HF of F is also interpretable in K of F. So group ring knows about the group F much more than the group itself. Group itself, definable subgroups are cyclic, as I said, multi-problem. But if you can see the definable subgroups in F which are definable in the ring K of F, all of them are definable, all reasonable. I mean, all finitely generated, all verbal, whatever you can describe in second order logic, and it's a lot. All of them are definable in this ring using just pure ring theory language, which is kind of strange, but that's what's going on. The same for free associative algebras. It's bi-interpretable with the HF of K. The free algebras and varieties are like that. I'm sorry. To interpret HF of K in the algebra is not very easy. So what we use is so-called the least superstructure instead of H of A. What is this? It was introduced by Goncharov and Yershov to study sigma computability, and it goes like that. So first of all, you can see the two-sorted structure A and all lists S of A with operation concatenation. And then you add arithmetic. And this is list superstructure over A. So you have structure A with all the predicates and operations in the language of A. You have lists with the concatenation. You have natural numbers with addition and multiplication. And you have a function L of S, which is just the length of the string. It gives the length. And there is a predicate T, which for string S and number I gives the i's coordinate, which is an element in A. So it picks the coordinate. That's the list superstructure, which is useful for sigma definability or sigma computability. But it turns out it's extremely useful for what's going on? Sorry about this. Press something which I didn't need to do. Yeah, it's here. What is not difficult to show that this list superstructure is bi-interpretable with HF of A. So you can freely use the lists instead of HF of A, and it's more convenient quite often. So it's different form of weak second order logic, which is kind of more to the point of standard kind of using tuples, coordinates, and so on. And the last class that I would like to explain, which are rich, are so-called existentially closed structures. There was, I don't know, 30 years ago maybe, or like that, maybe more, there was huge effort to study existentially closed structure in some classes of groups or rings or semigroups. And it was a lot of very good mathematicians who studied these structures, showing that first order, they were solving different problems, but main idea was that first order logic of existentially closed structures in these classes is very, very powerful. So you can do a lot of things. So what are the classes? The theorems they proved, of course, it's different proofs, but I just put it in one result. They proved that existentially closed object in the following classes of all groups, torsion-free groups, all semigroups with cancellation, inverse semigroups, skew fields, or division algebras now they're quite often called, associative rings, and many others. All of them are rich. That's what they proved. And every time it was a different proof, but the idea turns out to be, if you look inside, it's very India, another approach to the weak second order logic. It was distilled by Belayev and Tyson. They noted that was a core statement almost everywhere. And what was the statement? It's not the language Belayev and Tyson were using or the original authors. It's what I just put it here to explain. Starting with the structure A, you can consider another superstructure of finite binary predicates over A. So what is this? This is a set FBP. It's finite binary predicates over A. And you consider superstructure which has two sorts. Original structure A, this set of binary predicates, and the predicate which holds in the structure, it holds on AB and predicate H if and only if the pair AB isn't the predicate. It relates predicates naturally to the elements in A. What not difficult to prove? It's easy to prove that HF of A and FBP of A are absolutely bi-interpretable in each other. So this thing is the same as weak second order logic. And what all these authors did in the modern language, or in the language actually is what I'm presenting here, it's always they said that if you have the algebraically existentially closed structure A here, it's bi-interpretable with its finite binary predicate superstructure. Sorry, A is bi-interpretable, but it implies that A is rich. And then you can apply immediately weak second order logic and get all the properties that were proven in this paper using different tools. But now it sort of comes for free because it's a very powerful logic. A little story just to finish the talk. When I was PhD student of Myasnikov a long time ago, Myasnikov had an idea to, and we started to look into Tarski problems about free groups. And idea, so what did we do? We looked at this, Myasnikov actually was looking, and I was joining him. So it was decidability of the free group and also Watt's conjecture that free products preserve first order equivalence, elementary equivalence. And the idea was, let's enrich free groups or free products with something very, very small, some new predicate, such that it will help us to study the first order theory in the new language. And then we bring the information we've got here to the free group or free product itself. So what did we do? It's actually later I realized that Irina Huber-Dyson was doing similar thing. She was just getting undecidability results for free groups. But idea is you have a free group F, you enrich it using many things, but say either predicate, binary predicate, which says that there is no cancellation in the product xy with respect to the standard length function on F. Its fixed length function is fixed, so you can say whether there is cancellation between two elements or not. So P of xy is saying there is no cancellation. Or you can add equivalence relations saying that elements x and y, they have the same lengths. Or you can do a little bit things like that. And also you can do it for free products because there is a length function as well there, the standard length function. Within Huber-Dyson, she proved that in this case, the theory is undecidable. We didn't know, but we wanted to see what will be the expressive power of new language, of first order logic in F omega or G omega. What we proved, which was at that time, that was strange to me. So if you start with a free non-abelian group, and then you add a little predicate. And what you've got weak second order logic over F in full strength. So idea, so we wanted to try to understand how powerful first order language in F. It turns out, whatever we looked at, you add a little bit and suddenly you have everything. Weak second order logic, not a little bit more, but everything. The same for free products. For this, you need some group theoretic technique. If you have free product, add little predicate like that. You will have HF of the Stolling's pregroup, which associated with the free product. At that time, vision of by interpretability, we just showed they are mutually interpretable. But for the proof, I believe they are bi-interpretable. So these groups are, these structures are bi-interpretable, and these ones also. So they are rich. So you add in a little bit and getting a rich thing. I'm wondering whether the same thing holds for hyperbolic groups or not, torsion-free hyperbolic or some other things like that. It would be interesting to see. And I think I have 5 minutes for questions. So thank you very much.
Okay, thank you, Alexei. Thanks for the nice talk. Any question? Please welcome if you have a question. Question.
It's too late or too early anyway.
Comment.
Actually, maybe I'll ask something. So you were talking about weak second order logic, but do you get the same thing if you look at computable infinitary formulas? The interpretations in HF of a structure, I mean, that seems to be effective just in case there are computable infinitary formulas that define the interpretation.
So what, as I understand correctly what you're saying, for example, infinite disjunction or conjunction, you can use arithmetic sets, but also you can use just computable. It's the same power.
Yeah, CE sets work.
Yeah, exactly.
Yeah.
Sometimes it depends what from, suppose you would like to prove that some properties are definable in weak second order logic. As I mentioned, there are several variations. In some cases, one is more convenient, in other cases, others. What is possible to do, you can join them into universal. You can use everything. You can use infinite disjunction, you can use HF, you can use lists or finite predicates altogether. Which of course will be just equivalent to each of them.
Yeah.
But it's much more convenient when you try to prove something that is definable in a group, because you can use all of them simultaneously. And that's on the other hand, when you would like to prove that something is rich, you would like to use one of the weakest form of these superstructures, as you, for example, as you said, computably enumerable disjunctions. That would be good enough.
Okay. More question, comment? Okay, it seems no questions. So thank you again for the nice talk, and thanks all of you for participating in the workshop. We'll start today for first day of the workshop. We will meet you tomorrow 8 a.m. in Italian time, and you have a whole night to convert your time to check. So see you tomorrow. Thank you for all.
Thank you.
Thank you. See you tomorrow. Thank you.
Thank you very much. That's interesting talk.
Okay. Now I'll go and hunt for the shorts, see if I can figure out where they are.
Okay. Good night for some of you. Good morning for some of you. Yes, good night.